An autonomous electric vehicle and a sudden obstacle in the road. How did we avoid a disaster? Autonomy and electrification are mega trends for the engineering community. And yet, safety comes always first. How can we develop technology efficiently? The answer is with simulation. A model of the physics and algorithms is presented. Let's start with the battery. A battery with thermal behavior is connected to a DC-DC converter. The heat of the battery is taken away by a cooling circuit of water and glycol. And the battery is connected to an electric drive, DC to AC converter and the electrical machine, a differential gear, and then the vehicle. So then the vehicle includes the 3D tire models and the ability to bring in traction torque. Additionally, we can reuse CAD designs and bring in all the kinematic information that we need for the simulation. Let's have a look at the supervisory logic, taking in estimated time to collision and vehicle speed. The vehicle can experience 5 states: normal, with the torque gradient is 0, acceleration, positive gradient for torque, and then as estimated time to collision decreases, the vehicle enters braking, gentle, and swift, which are states of energy recovery. Kinetic energy is fed back to the battery. Emergency braking will occur when the hydraulic brake system needs to be active together with regeneration. The brake consists of a hydraulic pressurized oil circuit. So when oil comes in into the actuator, there will be a force exerted on the brake, and that will bring the vehicle to stop. And then finally, we have a speed regulation, a PID controller, reference of torque coming from the supervisory logic. And then the speed is regulated to match the desired speed. So how does regenerative braking impact in the situations below? Distance skipping, collision avoidance. When is emergency braking required to guarantee safety? First case, the vehicle encounters a mobile target and adjusts speed to maintain distance. At around 14 seconds, gentle braking is applied and the vehicle keeps distance nicely with the mobile target, as you can see in the animation. This is confirmed by the plots of position of the target versus vehicle and even estimated time to collision. Second case, a static target at 100 meters. The vehicle accelerates up to 45 kilometers per hour, but then brakes electrically over 15 seconds for a safe stop. It's really cool to see how that happened. Looking into the plots, we can see how the vehicle speed, battery current, and motor torque look like for the run. From an algorithm perspective, what happened? So went to acceleration, and then when the object was detected, then gentle braking was applied. The vehicle is slowed down, then finally stop. And then third case, a static target at 200 meters. The vehicle reaches 70 kilometers per hour. Due to the high speed, braking requires not only regeneration, but even the action of the hydraulic brake at 19.4 seconds to avoid a crash. So normal acceleration, and then we are going to see how the vehicle enters gradually all the braking states: gentle, swift, and finally emergency braking. The vehicle is stopped and then went back to normal. So this is the sequence and the plots in the time domain. And then even the different states that were experienced during the run. And here, if we zoom in at around 19.4 seconds, so then we will see at that point in time, the emergency brake had to be active. So is the design of electric autonomous solutions of interest? Do you believe in model-based methods for teaching? Or is more effective testing of software what you're looking for? In any case, you are very welcome to reach me and then consult the MathWorks homepage. Thank you very much.